We've taken a look at valence bond theory already. Now we need to look at a different bonding theory called molecular orbital, or MO theory, that's a little bit better at describing how bonds form and the way molecules form up to make the shapes that they make. So to begin, let's summarize valence bond theory. And in particular, remember that for valence bond theory, you need to first use VSEPR to figure out what a shape is. So is it trigonal pyramidal? Is it trigonal bipyramidal? Is it octahedral? Anything like that. Valence bond theory says that I get that shape by the formation of hybrid orbitals around a central atom. So for example, this phosphorus in the middle here that has 5 connections to chlorines is an sp3 D2 hybridization. Or this formation where this carbon is forming a triple bond with another carbon, those carbons are sp hybridized, and you've got 2p orbitals left over. And so because of that, valence bond theory says, well, these bonds are just an overlap of one atom's orbitals with another atom's orbitals, and the electrons live in the space in between. So a PCl bond is, as drawn here, the sp3, and I'm sorry about the typo there, that should be sp3d, not sp3d2. So it's the overlap of the sp3d on a phosphorus with the 3p on chlorine. That's the bond, and that's where the electrons stay. On the other hand, when I have multiple bonds, I have to break them down into sigma and pi. And so the way that that breaks down is that the carbon-carbon triple bond, remember, was composed of a sigma bond and then a couple of pi bonds. The sigma bond was the sp overlapping the sp. So the hybrids made the single bond because of head-to-head overlap. The pi bonds were 2p orbitals overlapping one another. And that was, instead of head-to-head overlap, side-to-side overlap. And that overlap, again, is the space where the electrons hang out. The thing about valence bond theory, though, is that it's not sufficient to describe the way molecules form up in their shapes. It's really bad at bond angles. Remember, we would say something like, oh, well, in this tetrahedral carbon, you know, in this methane, the bond angles were definitely 109.5. But all of a sudden, when I replace one of those hydrogens with a chlorine, and I leave the rest of them as hydrogens, the bond angles stop being 109.5. And it gets even more confusing when you get to higher order shapes. So for water, this bond angle is about 104 degrees, but when it's Se and 2 H's and the lone pairs, that bond angle is even different. It's a little closer to 90 degrees. Valence bond theory just isn't sophisticated enough to explain what in the world is going on with those bonds. And also what valence bond theory can't do is it can't predict why some compounds are more stable than others. So why are some bonds stronger than others? Why are some overall compounds more stable than others? Valence bond theory just can't do it. And it turns out that the key failure for valence bond theory in this is that it assumes that a bond is from localized sharing. So only 2 atoms, I'm sorry, this should not be 2 electrons, this should be 2 atoms only. The bond is between this carbon and this carbon, or the bond is between this oxygen and this hydrogen, or this carbon and this chlorine. Bonds are localized in valence bond theory, and that turns out not to be good enough. And so we turn over to MO theory to try and help solve some of those problems. So MO theory is different from valence bond theory in that all of the valence orbitals, right, go towards forming bonds. And then we just put them all in a blender and see what happens. There are energy considerations, so orbitals that are too far apart in energy aren't allowed to mix. Orbitals that are closer in energy are allowed to mix. If you want to learn about that, become a chem major. Come take quantum mechanics with me. We'll have fun and we'll learn about that. But the basic idea here is that orbitals on the same atom can mix. So oxygen could come into a molecule and it could donate and mix its own orbitals before bonding, or leave them separate for mixing with other things. Orbitals on different atoms can also mix, so the hydrogen and the carbon atoms can mix together orbitals. And the other thing about MO theory that valence bond doesn't do is that there's always a pair. So when I bring two orbitals together, they can mix in a good way that's stabilizing and it forms what's called a bonding MO, or they can mix in a bad way that's destabilizing and form what we call anti-bonding MOs. And we'll make a diagram that shows us how this works later and we can identify those things. But the basic idea then is that the valence orbitals come into mix and the valence electrons fill the diagram. And we use that to predict key properties like what the bond angles will look like after mixing and also like what the energies are. And the net of it is that electrons are kind of delocalized throughout the molecule depending on how an MO looks. And so the electrons belong to the whole molecule, not just between two atoms at a time. That's the key difference for MO theory. What I want to do is I want to look at three different kinds of MO diagrams right now. And I want you to know that what I'm showing you is to be able to identify features. I will never ask you to draw an MO diagram from whole cloth. Tell me who mixes and who doesn't. But I could give you an MO diagram and say, hey, is this a bonding orbital or an anti-bonding orbital? Hey, is this a sigma orbital or a pi orbital? Okay, how many electrons go in here? Those kinds of things. So don't focus on the way the MO diagrams look. Focus on what you do with them after you have them in front of you. So here we go. Let's start with the absolute most simple molecular orbital diagram we can have, H2. H2 is what we call a homonuclear diatomic, homo for the same, so an H with an H. Diatomic, two atoms. So this is a homonuclear diatomic model or molecule. And if we think about it, H2, remember we said everybody donates their valence orbitals. And so each hydrogen is going to bring a 1s orbital with it. And so in my MO diagram over here, you can think of it as divided into three wings. And you can think of a y-axis here as energy, like shown in this particular diagram above. So on the left here is one of the hydrogens, and on the right is the other. And what I'm showing you in these wings is the valence orbitals. So this is the 1s on hydrogen, and they're at the same energy because they're the same atom, right? There's a hydrogen over here, a hydrogen over there, so their 1s's are equal to each other. In the middle are the molecular orbitals. And the thing is that we have mixing. Like I said, there was a good mix and a bad mix, and we see that on the MO diagram by noticing that we can connect these two orbitals down to this line or up to this line. Going down in energy, right, is an example of constructive mixing. So these s orbitals mix in a way that reinforces one another. That's this add path here going this direction to make a bonding orbital. And these two little dots here represent the nuclei, so the two different hydrogen nuclei. And you can see that there's no separation between them. The color here for red and blue is just to remind you that these were two different hydrogen atoms that mixed together. You can see that that whole MO is just a big blob that keeps electron density between the atoms. On the other hand, there's this subtractive path, and you notice that there's this line that's here. This is what's called the bond axis, right? Because it connects the nuclei in the molecule. And this perpendicular line here is called a node, right? There's blank space where we change from actually one sign from positive to negative is the way that we think about it in quantum mechanics. But you notice that it divides the electron density into two sides. The presence of nodes is always a little bit or a lot destabilizing depending. And so we call that an antibonding orbital, right? And any pair of atom or any pair of orbitals, when a pair of orbitals mixes, you can stabilize and make a bonding orbital, or you can destabilize and make an antibonding orbital. And the way that I can tell antibonding is the presence of a star. The sigma here is because of the node, right? So sigma means node is perpendicular to the bond axis. It cuts the molecule up and down. It cuts and divides the nuclei from each other. If you see a node that divides the nuclei from one another, that's a perpendicular node, and that's a sigma, or that's indicative of a sigma node. So we know that there was stabilizing mixing, and so the sigma s down here is the bonding orbital, and the sigma star s is the antibonding orbital. We know that they exist, and we label them as such. The lower energy is always no star for a sigma, and the higher energy is always star for a sigma. Now, as far as the electrons, let's remember that hydrogen has one electron. So each of these hydrogens had one electron to bring to the party. So think about orbital filling diagrams. Remember those arrows up or down meant electrons. And so each hydrogen had one electron. So the MOs have to have two electrons. Just like Aufbau and Pauli exclusion principle and all that, we put two electrons down there. And then if we had the two electrons past that, we'd go fill more. So that's a full orbital. And the last thing we do is calculate bond order. So what we do is we count up, remember bonding orbitals, no star, and antibonding orbitals are star. And so we count up the electrons, and then we subtract and divide by 2. And so for this hydrogen, the bond order, there's 2 electrons that are in the bonding orbital. There's 0 electrons that are in the antibonding up here. And we divide by 2, and we predict that the bond order is 1. In other words, a single bond. Remember, if we drew a Lewis structure for H2, we would say H and H. It's a single bond. And so it's good that MO theory matches up with Lewis theory, right? Lewis theory and Vesper and valence bond aren't totally bad. There's a lot of good things about them. And so MO should match up with those things most of the time. That should be an exception when it doesn't. Let's practice this on a more complicated diagram. So here's a harder one. With O2, it's still a homonuclear diatomic because we've got the same orbitals. And this time, let's divide it up. Our oxygens are on the left and the right, and O2 is in the middle. And if we think about it, the valence orbitals are 2s and 2p. And you remember that when you drew orbital filling diagrams, you always drew 3 lines for 2p. And so this is where they will go. And there's 2s2, so 1, 2, and 2p, 1, 2, 3, 4. Same on both sides because these are exactly the same element. So the 2s's do the same thing that the 1s's did for hydrogen. They make a sigma and they make a sigma star. We would actually call them 2s and 2s star. Don't worry about numbering. The numbering is beyond your pay grade for this class. Now, notice something kind of fun with the 2p's. Do you see that some of them make this set of 2 lines and some of them make this set of 1 line? That's because there's 2 different ways that p orbitals can mix. Remember, p orbitals can point up and down, they can point side to side, or they can point in to out. And the direction of the mixing actually matters because we have one set of mixing, and that's this one up here, where the p orbitals mix head to head. And you notice that all of the nodes, here's my little dots for the nuclei, all of the nodes divide the nuclei. These are perpendicular nodes. So these are all sigma orbitals. P orbitals can make sigma MOs, right? So S orbitals always make sigma MOs. P orbitals can make sigma MOs. And that's what this is. This is a sigma and a sigma star. But there's this other mode of mixing here where the p orbitals can mix side to side or in and out. And so what we get is a different nodal pattern. This bottom one right here has a node, right? It looks like that little plate that they're doing. And you notice that that node has the nuclei in it. It doesn't divide the 2 nuclei up. So we call this pi because that type of node always gets a pi name to it. And this is lower energy because there's fewer nodes. More nodes, higher energy, more destabilization. This one we call a pi star because it's got 2 nodes. And so we actually have pi and pi star. And calling them sigma and pi is a deliberate choice. It matches up with Vesper theory. So Vesper theory says that sigma orbitals or sigma bonds come from head-to-head overlap. Hey, it's the same thing in MO theory. Vesper theory said pi bonds came from side-to-side overlap. It's the same thing here. It's just that Vesper was talking about localized overlap. MO theory is saying it's the type of mixing that goes on. So sigma and pi are still concepts that show up. Now, we had 6 electrons in each oxygen. So we have 1, 2, 3, 4, 5, 6. Now I have a set of 2 lines at the same energy. They're what's called degenerate. So I need to go 7, 8, 9, 10, and now I go up 11, 12. There are 12 electrons in that diagram. If I wanted to do the bond order, let's count up everybody who's in a starred orbital and everybody who's in a not starred orbital. So let's do the way that we're supposed to. Let's do the bonding, so the non-stars first. 1, 2, 3, 4, 5, 6, 7, 8. So there's 8 minus, and now let's go ahead and count the ones that are in anti-bonding, so the orbitals with stars. 1, 2, 3, 4. So 8 minus 4. And now we divide that by 2, and we get a bond order of 2. Hey, remember when we drew O2, O2 has a double bond and 2 lone pairs. The lone pairs in MO theory are a completely different thing. And in fact, I don't see any lone pairs on this. I see elements that are, or I see electrons that are in bonding orbitals and anti-bonding orbitals. The other thing that I see that's interesting, that's hidden in the Lewis structure, right? Everything here looks paired up. It looks like every electron has a friend with it and they're all in pairs. And so we might predict that this is what we'd call diamagnetic. Diamagnetic things do not respond to a magnetic field. They're non-magnetic. But when we look at that MO diagram, well, we see that there are 2 unpaired electrons up here, right? So the real molecule is actually what we call magnetic. It is magnetic. If I put oxygen in a magnetic field, it will respond. And in fact, it responds kind of interesting. Why don't you go ahead, pause the video, and Google oxygen tank in an MRI. Remember, MRI instruments are just big old magnets. And watch what happens to that oxygen in the big old magnetic field of the MRI. I promise you, these unpaired electrons are having an absolute field day. All right, let's look at one more thing. More fun is when the atoms that mix are not the same. So homonuclear diatomics meant oxygen with oxygen, or hydrogen with hydrogen, or boron with boron, right? HF, on the other hand, is a heteronuclear diatomic. The elements are different, and so the mixing rules change. And so you can see in our diagram here, right, the H has its 1s electron, and the F has 2p electrons. Where's 2s? Well, it's way the heck down here. It's so far out of the way that it doesn't have anything to do with the hydrogens, right? We call this non-bonding. It has nothing to do with anything else, and so it lives way down here. So there's fluorine's 7 valence electrons, and there's hydrogen's 1. And so you notice the way the energies are. It's the 1s on the hydrogen that mixes with the 2p's on the fluorine. And there's only one way that that's actually useful. That's if we have what's called the 2px of fluorine, the one that points right at the 1s, right? Something that mixes like this and something that mixes like this is useless. But when they point, they make this bonding orbital and this anti-bonding orbital. And they're sigmas, right? The nodes are here and they're dividing up the nuclei. So here's a sigma and a sigma star. And then these 2p orbitals on fluorine are boring. They are left totally alone. They can't mix with the s orbital because they're just wrong, right? This mixing and this mixing are useless. It's only this one that works. And so these here we would call 2p 2px, or sorry, 2p, yeah, 2p, no, 2py and 2pz. And then we just put NB in parentheses for non-bonding. We need 8 electrons here. We put them in 1, 2, 3, 4, 5, 6. And then the other 2 are down here. They're the 7, 8. So orbital-wise, we only count, right? Do not count NB. Non-bonding things don't form bonds, so we shouldn't put them in bond orders. So when we count our things that are in bonding orbitals, I find 1 and 2. There's nothing in starred orbitals. See, it's just hanging out here, empty. So my bond order is 2 minus 0 over 2, 1. When I draw that Lewis structure, I would put H, F, and I would have 1, 2, 3, 4, 5, 6. I'd have 3 lone pairs. This matches up, right? There's a non-bonding and a non-bonding and a non-bonding. We're recapturing a lot of the things that Lewis and valence helped us intuit to, but we're doing it in a better way. And we're trying to see more about what happens with the bonding in the molecules. And it turns out that when you do molecular orbital theory, you get much better predictions of what's going on. The bond angles come out right. The polarity of the molecules comes out right. These key pieces of information that valence bond theory couldn't pick up on get picked up on in MO theory. And so we stick with this for the best descriptions of molecules.